these people a few seconds, they should be able to see your presentation over there as well. There we go. I will go on mute. I wish you the best of luck with your presentation, Ilana. Thank you for presenting.
Okay, thank you.
And we are uploading the presentation, converting the file now. So momentarily it'll be there. And once it gets there, I will, and we're almost, look at that. Okay. And so I'm going to grant you presenter. Except that you're already set. So over to you, Ilana. So we are fortunate today to have Ilana Kopperman. She's a system safety architect at Novolai. Prior to that, she was a security consultant for the automotive industry, and prior to that, a security architect for Cisco. Her research institutes focus on software engineering methodologies and security engineering. And we're very fortunate to have her here today to talk about how one might configure a Linux kernel for safety critical applications. Thank you very much, Ilana, and over to you.
Okay, thank you, Paul, and thank you and to everybody at the back end. I think this is an amazing feat pulling this off virtually, so good luck to all of you as well. Okay. Okay, I also apologize in advance. I do have a bit of a problem with home IP bandwidth. I shut off everything that I possibly could, which would impact that, and I'm hoping we'll be. Anyway, here in the agenda, it says what I'm planning to cover. Maybe I'll add in the disclaimer, more on the disclaimer section, what I'm not planning to cover. I don't have any silver bullets, no plug and play solutions, which by magic will provide us with a safe kernel. No one size fits all solutions. We still have a lot of engineering work. What I do want to discuss today is really more of a call for action based on my experience in various contexts. I should also add a disclaimer. This is not any work that reflects directly any commitment or any particular product by my employee, but it is based on cumulative experience in my current employee, and in previous places of work. What I really want to come out for this is some understanding what the problem is, why we need a solution, and perhaps given the audience who should be in this conference, a call for action to get together and building on some basic ideas, which I would like to discuss here, to see how we move it forward, perhaps someday to reach guidelines, what I will be calling safety policies, and I'll talk about that a bit later, which will help us to provide a kernel which is configured and usable for a specific context in a safety critical application. So having said that, bit of delay. Okay, anyway, background, that was already mentioned by Paul. Okay. What are safety critical applications? I don't want to spend a lot of time on this. Is a little bit just for background. Safety critical applications have various unique requirements because of their context. In particular, my work is focused in the automotive domain, where obviously safety of the product has strong legal and other implications, which are binding and which provide very real constraints on the work and our expectations for the systems which we produce. Open source, for all the reasons that anybody in this conference knows, is familiar with, especially Linux, has huge advantages. But initially, Alex was interested into the automotive in safety critical applications. I shock. So conservative, well, the document waterfall type of outline developed. We're relying on a lot of proprietary software, which wasn't publicly available, source code, etc. And there were a lot of very, very serious constraints for safety qualification because of the legal and other implications. Okay, and this is just a general overall view. I don't want to go into details on that. On the hand, mindset and way of working than was expected in the past in developing safety critical applications. I'm mentioning this only briefly. I'm also involved in a group called ELISA, which is just trying to bridge that gap to develop tools, guidelines, and to help to be able to deploy Linux more effectively, more smoothly in safety critical applications. Typo here, missing the word critical, safety critical applications, but okay. Today I want to focus not on the general problem, on the aspects having to do with kernel configuration. And here I would like to bridge another gap on what we will call dependability, which is basically security and safety. And starting out on the work of trying to define how we can configure a kernel for safety applications. The obvious starting point was to investigate what has been done for security and also build on my previous experience. So there are two well-known and commonly used sites. There's a site called the Kernel Self-Protection Project, which has a lot of very, very nice ideas. And it's certainly something which should be consulted for any serious user. But what you see here in italics, these are quotes from the sites. It's pretty much what they call a brain dump of various options for a particularly paranoid system. Meaning if somebody really goes line by line and just configures their kernel exactly according to all of the guidelines there in the site, if they're working in any entity, they'll probably either get fired or switch to another project because it's going to be really, really over restrictive. And the site there, even though all of those recommendations for the kernel configuration have their justifications and good reason for being each of them to be chosen, there's no really clear guidelines provided how to measure your level of paranoia or what's appropriate for your particular use case and what should be used and when. And there's another site which is part of the kernel documentation, which provides also different recommendations on configuring the kernel. But here it's a little bit more structured. And they give, to begin with, something which is already a very positive improvement. They define certain criteria. Okay, so they say that if these recommendations, if you want to configure your kernel, you shouldn't just randomly go over, the kernel database and just choose whichever ones look nice, but you have to have some guidelines for making your choices. And if you want to configure a secure, here they're talking about security kernel, you have to choose those configurations which are effective. And these are the guidelines which they mention: on by default, require no opt-in by developers, have no performance impact, do not impede kernel debugging, and have tests. And they also agree, obviously, that you're never going to meet all of those goals, but it's at least an initial start for guidelines and criteria. Okay, so if we go over these guidelines, I would agree with the first three. I mean, you don't, and when we say affected, that means we have to understand what our goals are, and then we can judge if something is effective or not, if it achieves those well-defined goals. We have to deal with performance, and this I can tell you from experience, anything certainly having to do with security, if it impacts performance, then project management is going to be very quick about overriding the decision. So you have to be careful that you can make some statement about the performance impact and that it's within reasonable bounds. Otherwise, you'll be shooting yourself in the foot. You can't just make security or safety recommendations which hog the system. And any kernel configurations which you turn on should not impede kernel debugging, because we obviously can't deploy products which we can't debug completely. And this is more relevant for security because if we shut off every possible option of any type of debugging of the production kernel image, again, we will be shooting ourselves in the foot, and it's something which will not go well with project managers. The last three criteria, I will put them at much lower priority, on by default. It's no sweat. You can always, have it turned on. I don't think that should be a criteria for really a high priority criteria. Requires no opt-in by developers. If the developer can't enable, configure, somehow adapt their software to the requirements, then maybe they should look for another job. Okay, and have tests. We can always write tests, so I don't think that's a limiting factor. Okay, but the first three I think are very essential, and this is at least how criteria do we define for choosing the kernel configuration settings that we want to use. Now, the previous slide was talking about security criteria, but going back to our original topic here, we're now in the world of safety. And safety is a very different domain. And in many ways, again, when we talk about dependability of systems, we're talking about security and or safety, but they are not identical. And we will soon see some examples where we have to keep that distinction in mind. And it's important when we're talking about criteria to differentiate between security criteria and safety criteria. Safety is pretty much all about liability, and there may be safety experts, which I'm not a safety expert, in the audience who will disagree with me, but it's pretty much, if we want to pick one word which defines safety, it's pretty much about liability. Okay, which means basically we have to be able to give some kind of legal proof that we did the best we could to make our systems safe, especially in systems on which human life is dependent. Another thing which we have to have is traceability. That's a very important issue. It's very fundamental, because if we cannot measure it, then we really can't prove that it exists. And it's also, traceability provides, at the end of the day, the legal proof of that best effort, which I talked about before. And when we want to make any decision for safety, we have to have very well-defined and measurable criteria. For example, if we want to choose certain kernel configurations, we will have to be able to say, why did I choose this setting, and why did I not choose some other setting? And we have very criteria for those. So, and here, one of the subtle, okay, Luke might have, and thank you, you're a safety expert than me. I wanted one word, so I chose the word. Luke, 4 words, risk management of liability. Probably a more accurate definition. In any case, one of the fundamental in which security is much higher is of long living in justice where it's and lives it's safe we're not saying oops. Do you hear me? Do you hear me? Let me know if somebody wrote that the audio went out.
You're back again. We can hear you again. It's coming off and on. Are you perhaps presenting on Wi-Fi, or is your laptop a little busy as well? It sounds like it's on your client end. That anyway, we can hear you most of the time. If you can keep a little bit of an eye on it, sometimes you go out, but it comes back. It just takes a few 10 seconds. So we can hear you now. Please continue.
Okay. Thank you.
And we have just lost you again. We can't hear you
No,
anymore.
I have a serious problem with my home.
Yeah, you're coming on and off right now.
Hello? Hello?
Yeah.
I
We
don't
can hear
know
you,
what.
but you're breaking up. Go ahead.
We should have made it more clear that a wired connection for presenters would be a good idea. I realize it's not always possible.
Okay. Good enough. I'll remind a bit that it's enough here. That will I possibly embeddedly conference. Well, it was good enough.
I think you didn't you do your audio via phone for embedded Linux conference probably? But it's something we can offer here. It's okay. I think we can hear you okay now. Please try to continue, and then Paul or I will let you know. We can hear you now.
Okay, good. Okay, thank you. For safety, we need that traceability, and their ability to leverage information leakage, and therefore the focus open at the areas we will see a key difference right there. I don't hear.
We can hear you. You're breaking up a bit though.
Okay. Well, and I hope you'll be able to fill in the gaps a bit. Okay, so just to be a little more, and this is, it's not in some order or structure here yet. We'll get to that in a few minutes. Some standard basic configuration settings for security where I think steep criteria would match security criteria. For example, config dev k. I'm not going to spend time defining each setting and what it does, but basically dev k is a pretty basic standard configuration. Ability, right space, an obvious no-no production system, and 50 reasons as well. We don't want to be able to mix user applications with kernel applications, and certainly we shouldn't be able to directly do in any way corrupt kernel memory space in a production system. Okay, fortify source is also one of those basic kernel configurations for safety, which would be well accepted for security. I'm sorry, and it would be well accepted for safety as well, because it enables you to detect buffer overloads in many common string and other functions, and it's also something, again, which is basic to the quality of software which we expect to be used in safety applications. Okay, so these are we could first match those for security. On the other hand, quite surprisingly, and I found from experience when when dealing with real applications, there are many very fundamental security settings which hit a brick wall when it comes to safety. Okay, now the first one is config dev mem, which basically allows a root user to directly access physical memory. From security point of view, this is something which we normally would not expect to support for security purposes. But very often in safety systems, there are safety mechanisms which are built in, which want to be able to directly access physical memory in order to do certain testing, validation, to confirm the quality of the hardware, and blocking dev mem creates serious issues in that respect. So here we already have to deal with a question where it may not even be a black and white answer. There have been attempts to define, for example, to config IO strict dev mem. Again, I won't go into the details of what that enables, disables, but to have partial solutions which block some unneeded physical memory access. And this is already an open question. What would be relevant for safety purposes, what we can allow, and what we should be blocking for safety critical applications. Okay, I see somebody, Mel, thank you for the that note, and we'll get to performance later. I'm avoiding that right now, but you are definitely right. Performance, as I mentioned briefly before, is a huge issue when it comes to any configuration setting. And I think we should put that, I think the statement that you make can be made about most of the settings which we'll recommend soon, unless we start to say, if we want anything which we want to help us for debug, for logging, for tracing, or a lot of other aspects. And here we have this trade-off. And again, I'm throwing this out now. We can either say, okay, in my use case, I'm willing to pay the performance price, or, which is probably a better thing to be able to provide long-term, we may be able to develop more streamlined, less performance-hungry versions, which provide the value that we want for safety. But maybe when we use those settings for our applications, the performance hit is less can be put within reasonable bounds. So that's an open question, and it's something which we should keep in mind in the background for everything that we're talking about here. But right now, what I want to just point out here, that there are various settings, for example, such as the config dev mem, which are maybe essential for safety, even though normally from a security point of view, we would want to disable them. Another example is ELF core. Very often for safety critical systems, we want to be able to generate core dumps, because the core dump is going to be, if a car, let's say, for example, is in a crash, we want to be able to have some record of what happened before the crash, especially if it was due to a software failure. So, and core dumps that's one particular use case, but there are many other use cases where the core dump is essential for safety analysis and safety documentation. But very often for security, we would want to disable core dumps. There are means in Linux for generating secure encrypted core dumps. And similarly, we can find some way in the middle to support core dumps without impacting neither the safety, while supporting the safety as well as the security of our systems. Okay, so these are some examples. Again, I don't want to spend a little tight on time here already, but going into all these details. But each of these have a good use case criteria for being used in safety systems, even if normally we may wish to disable them from a security point of view. Okay, now one of the first ways, in order to be able to make some kind of structured decision about the kernel configurations which we want to use, my first shot at this was, again, based on work that's been done in the past by others from the kernel documentation site. They classify the security configurations in various groups. One deals with, the first group deals with attack surface reduction. Okay, here you even have some examples. These are features which can be enabled for attack surface reduction, and that's one category. A second category, which is very much relevant for safety, is preserving memory integrity. And the first one is stack protector. Again, if we're talking about performance impact, this always ends up with a huge fight because from a performance view, especially if it's strong, normally has a performance impact which is not acceptable, especially for embedded real-time systems. So that's the question, what do we gain? One of the things which we've done is to develop a customized stack protection. And this is something which may be looked into, how instead of going into stack protector strong, to go in the direction of stack protector safe, which would be some kind of compromise which doesn't impact performance to the extent where it gets disabled. But on the other hand, it does provide us with the assurance that we're looking for from a stack protection mechanism. Hardened user copy, also same thing. It has its issues. Also, it's architecture dependent and whatever, all kinds of ways where it can or cannot be used. And again, if we want to, perhaps the direction may be to develop some more specific configuration setting, which provides, again, if we have clear guidelines, what we're trying to protect, how we're trying to protect it, then we can enable that. Okay, here are some more examples for protecting kernel memory. One of the features which can be used, and again, it has its pros and cons, are the use of modules. Okay, modules mean that the feature is not built in, but it can be enabled as a loadable module, which is loaded when needed and perhaps removed when not needed. This has obvious security disadvantages because it gives the power to remove, to add code to the kernel, to a running kernel. But it has also an advantage that code which we don't want to be supported throughout the execution will be available only when needed. Okay. In addition, there's features such as signed modules, which has a very serious impact on the overhead of building our images and releasing them because of the need to support signatures and keys and all kinds of things like that. And so usually that's out of scope, but it is still an option which can be assessed. So again, if we want to be able to protect kernel memory, we can use various options, including defining access control, including clear guidelines, what parts of the kernel we want to be able to install as object modules. And module signing is something when in a and your previous I didn't react as that architecture specific is not accurate, but what I wanted to say is there are some issues in the implementation in different architectures which have to be taken into account, and I don't want to start diverging into that discussion. So signatures, I have never yet hit a project where it passed project management. And believe me, I've dealt with a lot of projects over the years. The project managers get totally go off the deep end when you start talking to them about having to support in their build systems all the necessary keys and deploying them and releasing them to all the different test teams. There's a huge logistics overhead involved, nothing to do with engineering or Linux. Okay, and that creates a lot of problems. So again, I've never managed to get that by project management, and believe me, I've tried over the years. Okay, but anyway, again, that's a side discussion, and if anybody has some magic which can help me for my next project, then I'll be very happy to discuss that offline. Okay. In addition, going back still to the kernel documentation site, there are discussions of probabilistic defenses, including KASLR. And here, again, I'm not going to the diversion that KASLR in theory is a great idea. In practice, the implementation is very limited and doesn't give us any real security guarantees. So we would need some investigation on how effective current implementation and support for KASLR is. There are other features which are have less dramatic impact, such as slab free list random, slab free list hardened, which can be effective. And even when we're dealing with information exposure, information leakage, some features which are also relevant for safety critical system. Okay. Kristen, I take that as a call to action. I'll be very, very happy to see moving forward on both together. Security was my first love. I've been in security architecture for many, many more years than safety architecture. I'm trying now to bridge that gap and to help bring safety architecture to meet in the middle together with security architecture and keys. That's exactly the type of what I'm looking for, how we can go and to define settings which take into account, and that's really one of the key points I'm trying to make, take into account the different considerations, the different well-defined, we should have well-defined criteria for safety and security, and to have appropriate configurations which can be used, and then we can come up with probably very clear guidelines for their use. Okay. Having said that about the security classification, I'm mentioning a classification which I'm quoting from ISO standard 26262, which is sort of the Bible for safety at automotive systems. They have a concept which they call freedom from interference. I'm not going to formally define that, but freedom from interference deals with, we want to be sure that we have two, if for the sake of this discussion, we're talking about software elements, it could be either software or hardware, but two different elements that don't conflict with each other, interfere with each other, and which could then lead to the violation of some safety requirement. Okay, and if you see the list here, I'm not going to go into the details, but it basically, the standard identifies three key areas where potential interference can come into play. Interference in timing and execution, in memory, and we saw the bit of that when we were talking about security, and in exchange of information. Okay, so this is sort of a, I don't know, what it looks to me sort of like a Google search type of shopping list, that somebody just made a list of everything that could possibly be available. And Alexander, I like your idea. I'll look into that. You're right about that. We've used both, but I never really thought of comparing it, so it's a good idea. Thank you. Okay. But these are criteria for defining areas where, again, if we're going back to the kernel, it's not obviously relevant for kernel configuration, but if we want to build our kernel so that it helps us at least to protect memory, to protect exchange of information, to provide some kind of enhancement, let's call it, or ability to assess the quality of our concurrent programming in a general sense. All of these types of features are relevant and very important for safety systems in the automotive domain. So the first area of work which is going on, just as a side, ISO 26262, which I mentioned before, it's domain specific. In many ways, it's over restrictive, and it's hard for automotive manufacturers to comply with it, but it gives us also some kind of baseline. There is work being done, and if anybody's interested in hearing more about that, they can come tomorrow to the Dependability micro conference. There's somebody, Shua Khan, who is leading an effort to derive classifications, categories from the CWE. And her work is expected at the end of the day to help define the anchor, which we're looking for here, for classification of safety configurations. Okay, and this would be for many other areas as well. Okay, I think my time is going up. I'm going to skip over the next slides. Okay, there are debug features, which again, I won't have time to go into, but each of these have their advantages and disadvantages, mostly dealing with performance, and they have to be very carefully judged. And again, maybe we can think of developing debug features which have less of a massive performance impact. The other features, which I call them passive safety features, because they're used for offline testing of the production image, because they have a high performance impact, but they do give some insights into the safety of the system, even if they cannot be enabled in the actual production image which goes out. And other features, again, I'm just skipping over these, which have different applications. Okay, and what I wanted to finish in the last 5 minutes is a little bit about my vision for what I call a safety policy. I think people should be familiar with what we call security policies. And when we define a security policy, that's a set of rules which help us to configure security decisions, for example, for access control. And it's a well-documented way of saying we made this choice, why we make this choice, and why we did not choose some other option. Similarly, what I'm looking for is to define safety policies, which means not every safety critical application has the same criteria and the same requirements. And it would be nice if we can have a way of defining a safety policy and using that to be able to judge what we actually are, the choices which we make. I hope I'll be able to get this chat afterwards and follow up afterwards in email or otherwise, because there's a lot of interesting stuff going on which I don't have time to go into. Okay? Okay, thanks. Okay.
We'll get it to you.
Okay, thank you. Thank you. There's loads of, wow, fun stuff. That's what I'm looking.
And I would
Okay.
also encourage the people that are asking why can't you do this to find out from Ilana why it is that there's a problem.
Yeah, yeah. I mean, init analog was a nice idea, and again, I haven't looked into that. That's why I mentioned it. But other things we could discuss. But okay, we'll leave that later. I just want to finish the last two slides. And basically, what I'm looking for is that we can define a safety policy, which first of all would be more of a sort of a management type of decision on the particular application, and to say these are our criteria. This is important to us. This is where we can bend a little bit. This is where we need to be more restrictive, and that will provide the criteria and based on which we can make decisions for kernel configuration and perhaps other features as well. Okay, and that could help to set up some kind of default configurations. Which sleeper has the right to afterwards override any default decision, but then they would have the obligation to make some justification why they overrode a particular decision, but it would help to pull in some default set which is well justified and well defined and well founded in research.
Just you got 2 minutes. I'm pretty sure you're keeping track of time, but I wanted to
yeah
get in there.
Yeah. That's why I'm running quickly and I skipped there. And perhaps long term, we can go into something which I call Linux safety modules, similar to LSMs for security. And they will provide those tools, criteria, and guidelines which will help us to pull in safety features in the specific context of the use case at hand. Okay. So the next steps really, and that's where I'm finishing now, is to take this forward. And this is something which I have not done. Okay, this is something I've been dreaming of. It's more of a vision, but pulling together those safety policies, using those to classify kernel configurations and to populate those policies with default settings, to define sets of new features, new configurations, which will be relevant in specific safety policies, and helping to support long-term deployment and maintenance. Okay, this is sort of a dream. What we've been doing till now is based on more ad hoc type of intuition, using existing kernel configurations, writing patches for customized, new features, but not as a formalized safety policy. And in the world of safety, that requires a lot of justification for safety assessment, which is a problem. Okay, so if anybody wants to contact me afterwards, okay. Yeah.
Thank you, Ilana. We have time for a question if somebody has one. Not hearing one though. We did have some excellent questions and comments in the chat. And
right, and I will try to follow up afterwards. Maybe I'll contact you afterwards and see how's the best way to do that here. Okay? Perhaps in one of the hacking rooms or whatever. Okay?
But what I'll do is I'll copy and paste the chat and send it to you. And if you, I'll happy to set up email contact if need be. And thank you again. Excellent talk. Very thought provoking, and there's a lot left to do. I agree with your last slide, especially with all of it. Important work.
Okay. Thanks. Okay. Enjoy,
all
everybody.
Right. All right. And at this point, it's time for preparation of the next speaker. I'm going to take, we had some technical difficulties at the beginning of the talk, which had the side effect of removing the uploaded slides. So I'm going to re-upload the other two presenters' decks.
Okay, we're almost ready to start our next conference on course scheduling presented by Vineet, Julian, and Joelle. Joelle, I'll make you presenter. And
yeah, Vineet is actually going first. Let me check whether he's joined or not yet. Yeah, he seems to be joined. Yeah, there he is.
Yeah, I'm.
Awesome.
Okay, so I'll make you presenter, Vineet.
Thank you.
Or sorry.
Yeah, the way we are planning to do it is like Vineet will be presenting and switching slides for the rest of us. Yeah.
You are presenter.
Okay, great. Thank you. Shall we start? Okay, cool. Hi all. My name is Vineet Pillai, and I work for Microsoft. Today, me along with Julian and Joel will be giving a small talk on the course scheduling feature and its current status. So course scheduling feature development has been going on for the last couple of years, and we have been presenting at LPC for the last 2 years about this feature. So today we'll be mostly focusing on the current state, but I have some few intro slides for who are new to this feature. So before getting into course scheduling, a brief history about the side channel attacks. That is the motivation for course scheduling. So as we all know, we have CPU vulnerabilities like L1TF and MDS, and the suggested or the recommended way of fixing this issue is basically to turn off SMT. But there are production workloads like cloud and various other workloads which would hurt if we turn off SMT. So the thought process was like, can we still keep SMT on and then try to mitigate the vulnerabilities? And that's how the idea of course scheduling was born. So coming to the concept of course scheduling, the idea is like the scheduler will have a core-wide knowledge of what is schedulable and what is trusted, those kind of things. And then the scheduler will make sure that only trusted tasks get to run on a core at concurrently at any time. So if the scheduler sees that a sibling does not have a trusted task, it will basically force it idle. It's just like turning SMT off. That way we can make sure that trusted tasks are running together and no data leak is happening because of a trusted task, a task running with an untrusted task. So the idea is like we basically tag processes or we group processes into trusted groups, and the highest priority task from a core is selected first. So since the scheduler now has a core-wide knowledge, you take the highest priority task from a core, and then go to each sibling and find a matching task or a trusted task based on the highest priority task, and then schedule them together. And if it sees that there is no trusted task on one of the siblings or one or more of the siblings, it will force it to idle, which is similar to turning the SMT off. Coming to the implementation details, we have, so how do we do this is basically every process has a new 64-bit value called a cookie. And the group of trusted tasks all will have the same cookie value. That way the scheduler knows which process can be trusted when it selects one process. And the run queue has a new RB tree which houses all the cookie tasks and it's ordered based on the cookie value. And this RB tree is basically used to efficiently and fastly search the run queue for a matching task. So as I mentioned before, you have you select a core-wide highest priority task, and then you need to go to each sibling and find a matching task. That's where this RQ comes into picture. Okay, that much about a refresher or the introduction. And now we are going to the current state of course scheduling. As of now, we are in the V6 in the mailing list, and it's based on 5.7.6. So the first 3 iterations were basically about bug fixing, performance optimizations, crash fixes, etc. And V4 and V5 was about fixing the fairness issues. V4, we were mostly focusing on how to compare 2 tasks across the CPU. CFS doesn't was not really designed to have priority comparisons across the CPU, because since we now keep track of the core as a whole, we need to compare the priorities to decide which is the highest priority process, and that had fairness issues. So we came up with the idea of core-wide min vruntime, using which you have a baseline vruntime now, and then you could compare efficiently, but it also had issues. I'll talk more about that later. V5 was mostly about load balancing improvements. Load balancer was not aware about the core scheduling feature, and due to which it would migrate tasks that are not compatible to a CPU, and that would cause fairness issues. And on V6, we were mostly doing cleanup with eyeing for upstreaming and working on documentation. And one of the major patches that we had was about kernel protection. So even though you have 2 trusted tasks, one task could go to kernel, and that becomes kernel runs with an untrusted process. So we need to fix that. This will be covered in more detail in the coming slides. So as I mentioned about the V6 status, we got a good round of comments from Peter during V5, and the majority of the changes were about code cleanup, and the other thing was about documentation. One of the gaps that we had was we didn't have a good documentation, and the recommendation was to come up with documentation about what works, what doesn't work currently, what are the drawbacks, and how it works, etc. So V6 currently has a good documentation in place. And for testing, we found out that performance is better than no SMT. Like, it's better than turning off SMT for most production-like workloads. There were a couple of synthetic tests like UPerf, which shows performance degradation, which needs some investigation. But other than that, most of the performance tests that we did for production-like workloads were showing good improvement compared to no SMT. And I would like to list the gaps that we have right now. The major gap that we have is cross CPU comparison, priority comparison. We have this concept of core-wide min vruntime, but that also has fairness issues, which I will explain later. And load balancer needs some work to understand the core scheduling feature and migrate process accordingly. So starting from the initial version of core scheduling till V3, we saw a lot of hot plug related crashes. Like, if a hot plug event was happening, then we saw a couple of crashes, and we had iteratively tried to fix it whenever we saw the crash, and those became complex over time. And in V5, the fixes seem to be unmaintainable. So we removed all the hot plug related fixes in V6, which brought back all the crashes. Post V6, we have a consolidated fix for this after doing investigation into why this happens. So we have a fix post V6 for that. And as I mentioned before, the kernel protection also has a fix post V6, which we'll explain in the later slides. And another major gap that we have is still we don't have a consensus on the user interface. The V1 started with a CPU controller. The interface that we had was a CPU on the C group CPU controller. So we have a tag file in there, and that tag file is used to actually group processes in a C group controller. But it was a quick fix or a quick prototype. It has a lot of issues. So we are still discussing, and then tomorrow's MC will have a major discussion on how should we go about the user interface or the APIs. Now, the major gaps that I mentioned before, I would like to go through one by one. The first thing is the runtime comparison. As I mentioned, we need to compare cross CPUs, and vRuntime is not a good metric when we want to compare priority across CPUs. So in V5, the current solution was to have a core-wide min vRuntime. Whenever this is how it works. Whenever core scheduling is enabled, one of the siblings min vRuntime is chosen as the core-wide min vRuntime. And from then on, all NQs will inherit that core-wide min vRuntime. Since we have a core-wide min vRuntime, the comparison becomes much easier because we have a baseline now. The updation of the min vRuntime works in such a fashion that you take the max vRuntime of all the siblings and then sync it to the core-wide min vRuntime. But it does have fairness issues. The fairness issue is basically when two compatible tasks are running on the core, and one has a higher weight than the other. So the lower weight process, the vRuntime progresses much faster than the higher weight process. And as I mentioned before, the highest vRuntime gets synced to the core-wide min vRuntime, due to which the core-wide min vRuntime will always be the highest vRuntime value of the whole core. And if a new NQ happens, it gets the highest vRuntime value, and that gets starved. To explain it more pictorially, consider this case of HT0 and HT1. Task A has a lower weight, which is on HT0. Task B has a higher weight, like about 10 times more in this particular example, which is on HT1. And they both starts with a core-wide min vRuntime of 100. And then it starts running. And after some time, as you can see over there, the vRuntime of the task A, which is a lower weight process, gets to something like about 1100. It's like 10 times more than the task B, which is at about 200. And suppose a new process gets enqueued, which is incompatible. If you see the cookie, task A's cookie is cookie X, task C is cookie Y. So it's incompatible with what is running on the core currently. And task C gets enqueued, and it inherits the min vRuntime, which is currently 1100. And task A gets scheduled out. So now we have task C on HT0 with vRuntime 1100, and task B on HT1, which has vRuntime of 200. So there's a huge gap here, due to which, and they are incompatible. Task C is incompatible with task B. So task B gets selected, and task C is forced idle to simulate the SMT off case because they are not compatible. And task B need to catch up to the vRuntime value of 1100 before task C gets a chance to run. So there's a huge starvation, as you can see there, due to the fact that we have a core-wide min vRuntime. This is a huge issue, and Peter had a solution to this in the mailing list. So the idea is when a sibling is forced idle, it basically stops running, like the CPU is like switched off, and its vRuntime doesn't progress. So it's like a single CPU. It's a single run queue from then on until the forced idle CPU comes back and runs something else. So the idea is when a sibling comes out of the forced idle, its vRuntime stalled for a specific amount of time. So it needs to sync up with the CPU that was running. So when a forced idle CPU comes back to running, it syncs its min vRuntime with the CPU that was running, and then it continues independently. Since the vRuntime is independent, you don't have any issues from then on, and when it goes back to forced idle again, the same logic continues. But there's a downside to it. If you have more than one SMT, like if you more than 2 threads in a core, then it would be difficult, because this basically assumes that you have two threads per SMT, two threads per core. But we need to think about how to actually extend this notion to SMTX. The second gap that I mentioned was about load balancing. Load balancer is currently not aware about core scheduling. We have a minimal patch out there, like to check for the cookies and then migrate tasks accordingly. But that has fairness issues in the sense that it's very similar to what I mentioned about vRuntime. it doesn't take into consideration the weight of the processes. So there is a chance that a higher weight process can get starved. So we need to work on the load balancing fixes as well. After V6, there have been a couple of patches posted upstream. Just want to discuss that as well. One thing is about the hot plug fixes, and the second thing is about the kernel protection that I mentioned. Coming to the hot plug issues, till V5, till V3, we had hot plug related crashes when a CPU is coming offline or online while CoreSCHED is being enabled, and the patches grew big over time and it became complex. So we removed all the patches from V6 and started from scratch. The problem is this: Picnex task needs to iterate through all the siblings, and so it does this by using SMT mask. And SMT mask can change dynamically while Picnex task is running. The two ways it can change dynamically is current CPU might be already offline and schedule gets called for the current CPU to go to idle thread, or during online it can be called through for the migration thread. But at that time, there is a chance that SMT mask is not yet updated. So this really confuses Picnex task because it gets called for the current CPU, but we don't consider the current CPU. And the second case is while Picnex task is running, SMT mask can change underneath us. So we don't have a way to actually identify this. So due to these two cases, Picnex tasks get confused, which later leads to a crash. And till V5, we were checking CPU offline, but that had corner cases which led to hangs and crashes. So the current fix that we have right now is to fix both these cases. Like if current CPU is not there in the SMT mask, you deliberately, explicitly consider that during the Picnex task loop so that we don't miss out on that. You need to correctly schedule idle if it's going offline, or correctly schedule migration thread if you're coming online. Secondly, if there are about 3 loops in Picnex task, so all these 3 loops go through SMT mask, and between these loop, if SMT mask changes, you need to identify that and start fresh if SMT mask changes. So there is a bounded retry logic that we have in SMT mask in the Picnex task. So these 2 fixes solves the hot plug issues. Now I would like to hand it over to Joel to actually describe about the kernel protection feature in core scheduling.
Give me 1 second. I'm getting my camera set up. Yeah, unfortunately, my camera decided not to work, so I'll just have to be on audio, but that should be okay, I think. Okay, so kernel protection. So as Vineet was saying, core scheduling is intended to allow hyperthreads inside of a core to safely execute side by side in a core. So basically, it's protecting user mode on one hyperthread from user mode on another hyperthread. And if the tasks can trust each other, then it's okay for user mode and user mode to run on both hyperthreads on the same core. However, if one of those hyperthreads enters the kernel through a syscall, or it receives an interrupt or something like that, then we are exposing the kernel on one hyperthread to user mode on another. So even though the 2 tasks on the hyperthreads trust each other, we still the kernel still should not trust the user, because the kernel can access all kinds of pointers and do all kinds of walking and all that kind of stuff. And we're at risk of exposing sensitive kernel data that is accessed by the kernel. So we need to do something about that to have a working core scheduling solution. So that has been our effort. So can we go to the next slide? So the way we do it is we try to track. We try to add a notion of the entire core entering and exiting the kernel, not just any hyperthread. So we try to we have this thing called the core-wide unsafe state, which we track by counting. So as soon as any hyperthread enters the kernel, we consider the whole core to have entered the kernel, if you will. And we do that by counting. And we also count to make sure that if any hyperthread entering the kernel is not the first one to enter the kernel on behalf of the core, then that should be tracked as well, so that we know when to turn off the core-wide unsafe state correctly. So in this diagram, you can see that HT0 enters the core-wide unsafe state through a syscall, and HT1 is the last one to exit kernel mode, and so the whole core exits the core-wide unsafe state after that. Next slide. So how do we track this? So the way we track it is we track all user mode entries and exits, idle entries and exits, and VM entries and exits. And we have seen that this has this handles all the corner cases and is stable and gives us lets us handle all reasons why we might enter or exit the kernel. Next slide. So what do we do when we enter this core-wide unsafe state, right? So what we do is we scan all the hyperthreads, and if we see that any hyperthread is running an untrusted task, that is basically a task that is tagged with a cookie, we send it an IPI. So basically, we're trying to force all the unsafe contexts on the hyperthreads into the kernel. So all of them enter the kernel. And then once they enter the kernel, we will wait till it is safe to exit the kernel on the hyperthreads. Next slide. So I just want to mention that we do not send IPIs all the time. We try hard not to send it. There might not be any need to send. For example, in this diagram, HT0 gets an IRQ, so it enters the core-wide unsafe state, but HT1 and 2 are idle, so there's no need to send an IPI. And that is sufficient for what we want to do. We do have to wait, as I was saying in the last slide, we do have to wait. Once hyperthreads are in the kernel, we have to wait until the core exits the unsafe state if what is running is going to be unsafe, right? So in this diagram here in pink, you can see that's an untrusted task that receives an IRQ, and meanwhile HT1 and 2 have entered the kernel as well, and so HT0 has to wait before it can return back to user mode. Next slide. One of the troubles we had in earlier series was protecting soft IRQs, but with this technique of monitoring entry and exit into kernel, the soft IRQ problem also automatically gets taken care of. So that's no longer an issue. Next slide. As I was saying earlier, we have to track when we enter and exit idle as well. As you can see in this example, we have HT1 making a syscall, and the syscall doesn't complete. It goes to sleep in the middle and enters the idle loop. So by tracking the entry and exit into idle, we track also when it is okay to exit this core-wide unsafe state. Next slide. So the whole patch series to do this thing is posted to LKML. We've done testing on this, and we don't see any performance issues. It's looking good. And in the next slides, Julian will talk about performance testing as well. So with that, over to Julian.
Hi. So I'm Julian. I work at DigitalOcean. So for this V6, we did a lot of VM-based performance results, so mostly virtual machines. We know there are lots of other tests to run, and we are running them, and we have an issue with we are currently investigating on the mailing list. But I wanted to share this part of the results because that was one of the big use cases to start working on the core scheduling feature. So the idea is that we don't want VMs to be able to share cores because we want to make sure they are all on their own trust domain. So the test environment is 2 physical CPUs of 18 cores, so it's 72 hardware threads on Skylake. It's all based on KVM and on the latest branch with the system call and IRQ protection Joel just described. We start the workloads with CloudBench, which is a tool to help us provision and control tests and make reproducible experiments. And all the guests are running on Ubuntu 18.04. So we have 3 main classes of tests. So I will first describe them and then show the results. So the biggest one we have is the TPCC VM. So it's a database benchmark. It's designed to be somewhat realistic use of a database. It's not just hammering the database on single request. It uses lots of various transactions and select and inserts. We have one database VM on each of the NUMA nodes. We have 96 also the somewhat idle VMs floating on the same NUMA node. So it's comes down to a ratio of 3:1 overcommit ratio of CPUs to hardware threads. So the noise VMs are just meant to just generate scheduling noise. So they just are processes that are typing 15 seconds, collecting metrics, sending over VPN, and repeating this process. So across 192 VMs, it makes a lot of scheduling noise. The TPCC workload is interesting because it's a mix of CPU, networking, and disk activity. So we get lots of interrupts and lots of noise. It's not just a synthetic benchmark. And we run the client VM on a separate physical host, so it's not interfering with the workload, and it's using the real networking interfaces, not loopback. And each of the client is running with 48 threads. So we have one client for each database server. If we go to the next slide, we see the other tests. So this one was a mix. This one is LinPack. So LinPack is a really pure CPU intensive workload. It's a matrix inversion in parallel. So in the first case, we have 3 12 vCPUs LinPack VMs on one single NUMA node. So it's 36 vCPUs on 36 hardware threads. So it's a ratio of 1:1 vCPU to hardware threads, and it becomes a 2:1 when we disable hyperthreading. We also run the same test with 6 12 vCPUs LinPack VMs. So this is the same issue, but this times we have 2:1. So two vCPUs per hardware thread, becoming 4:1 when we disable hyperthreading. And we also had the four vCPUs virtual machines running NetPerf server, so just networking, pure networking workload with the client running on a separate host as well. But this one I didn't put the charts because there is no impact between the 3 configurations. So the goal for us is to compare the baseline numbers. So what is currently the performance on that specific kernel? What happens when we enable core scheduling? So each VM only runs on its own set of CPU and can only run at the same time on the same core with the vCPUs of the same VM. And what happens when we disable hyperthreading? Because that's the main point. We don't want to introduce this big feature if we can just safely disable hyperthreading, because that's the safest solution. But we clearly see that there is a major impact for at least this kind of workload. And we know lots of workload that are impacted by disabling hyperthreading. So that's why we trying to see if we can have core scheduling improve the situation while remaining safe. So if we go to the next slide, we see the results for TPCC. So this one, like I said, is the most impacted by the feature. It's around minus 46% of transaction per second decrease on average. It's a really noisy test. At the end of the presentation, I have a summary table with standard deviation and the real number, so you can just dig a bit more, but it's just to give you an overall idea of this one. So this one is, like I said, mix of CPU, networking, and disk, so lots of interrupt, lots of context switching. But we still see that compared to no SMT, so disabling hyperthreading, it's still much better than disabling hyperthreading when we enable core scheduling. If we go to the next slide, we have the LINPACK workload. So this one, like I said, is pure CPU. And as soon as we enable core scheduling or no SMT, we are now over subscribing the CPUs. And we see that the impact, again, for enabling core scheduling is less than the impact of just disabling hyperthreading. If we go to the next slide, we see the same test, but this one is 2 to 1 to 4 to 1. So we start already overcommitted, and we end up with twice as more overcommitted. And this one is interesting because you can actually see that core scheduling gains some performance compared to baseline. And it's not the first time we see this when we run LINPACK. It's common that LINPACK benefits from having proper scheduling aware based on hyperthreading, because it benefits from sharing the caches. So it's not the first time we see that if we group LINPACK tasks on the same core, they really gain performance, and that's what we see here. In the baseline, we have access to all the hardware threads on all the cores, but the load balancer doesn't make by default good decision, and we don't benefit from having core scheduling, where having hyperthreading. But with core scheduling, we actually benefit from having hyperthreading for this workload, and also gain security. And now we see with no SMT, it's much worse. So the next slide is just the summary of the results. If you want to dig, like I said, those tests are pretty noisy, so it's just to give you an overall idea. We know there are worst cases, like I said, the UPerf example we are investigating on the mailing list is one of them. But for the VM-based test, we clearly see a good benefit from having core scheduling compared to disabling hyperthreading while still remaining safe. So if you have any questions, I think that's the end of the talk. So feel free to ask. Thanks.
Any questions?
Hey, hello. This is Dario from SUSE, if you can hear me. Yeah. I typed something in the chat, but I can ask here. I can ask also here. I was just curious about how the tagging was done for the VMs. So all the CPUs of each VM are the same, were in the same group and have the same tag, I guess. And also whether you were tagging all the VMs, including the noise ones, or just, let's say, the ones where the actual benchmark was running.
Right. So each VM is in its own tag. So they all have their own groups. So they are not trusted with each other. So that's the biggest one. And the vCPUs are tagged from the same VM. The vCPUs are tagged also with the vhost task from the VM. So all the VM processes are in the same group for this test.
Okay, thanks. And all the VMs were tagged, including the one where the only noise. Okay, thanks.
Yes. All the VMs are tagged. That's the goal, is to make sure all the VMs are excluded from each other.
Oh, does this work? Oh, Mark, you want to go first?
Yes, please.
Right.
Just looking back at slide 18, when you say about sending an IPI to bring untrusted tasks out of user space into the kernel, obviously there's some latency between entering the kernel, running the code to send the IPI, and that other core receiving the IPI and entering the kernel, where you're still concurrently running user space on HT0 and kernel on HT1 in this example. So how much code is actually running on HT1 in that to get to that point where you can send that IPI? And how is that constrained such that you're not potentially leaking kernel data in shared buffers?
Joel, you are muted.
Yeah, so I was saying that we thought about that already, and what we have seen is that the hyperthread enters the kernel pretty quickly, like almost instantly. This is what we discussed on the mailing list as well, that it's instant. Now this is only on x86, so I don't know if like on ARM systems this will be different, but this is what we observe. And then the other thing was we thought it's probably a little overkill and not worth handling because we don't see the such delays. But even if we did, we've been told like not to look for like a perfect solution and add a whole bunch of overhead, but like look for like a practical solution that makes it more safe and handles like 99% of the use case. So we're not looking for 100% perfection. Yeah.
Oh, sure. Just to make that clear, because I do think there is a window there where if, for example, you're getting out of the KPTI trampoline into the kernel in order to be able to run the necessary code in order to send an IPI, you're running a reasonable amount of code. There's a reasonable amount of like kernel addresses that can potentially be leaked into shared buffers there. So if you really have a malicious process that's running, like you've got two malicious processes cooperating together, where one is just repeatedly entering the kernel and one is just scanning buffers, there is still a potential for data leakage there. I think it's important to make that clear.
Okay. There was a similar issue even before kernel protection. Just for core scheduling to work, you have to force idle like another. There's a chance we have to force idle another CPU, and that also happens through an IPI. So did you have any thoughts on that? There's a window there as well, right? However, on x86, we have not seen anything like that.
Yeah, that's a known limitation as of now, but in x86, as you mentioned, we haven't seen that, but we might need to profile it and see how much of a time lag is there between the IPA and then the other task switching, and then maybe we need to take steps. But as of now, we haven't done much investigation into it.
Sure. I guess my main concern wasn't so much the delta between sending the IPI and the other task switching, but the delta between entering the kernel on HT1 and then issuing the IPI. There's presumably a large number of instructions you have to execute first.
Right. Yeah, I see what you're saying. Yeah.
Anyway, thanks.
All right. No, that's fine. So I've been playing around with the patch set for a while, just a couple weeks ago for like a week. And one of the things that I noticed is that, well, two things actually. First is that HR fixes doesn't work at all with the cost getting patches. I have a couple of patches for that too. They do base enablement, so I'm going to send them as soon as I get around to it. That's just a note. The other one is the more interesting one, and that's one of my test cases that I've tried to analyze things on. Was basically trying to simulate something like the HWLAT latency tester in the kernel, just in user space to make it easier. So basically it's hammering the CPU for a read TSC, try to find out how long it wasn't running, basically being scheduled out for, and then bounces back and forth between the different threads in the system. And that means from a scheduler point of view, what you're getting is, if you're doing a virtual machine, or in this case, just a process, what you're getting is a lot of idleness that's unfairly distributed. So you have a process that basically consists of two different threads, and those two threads may either be hammering the CPU for a while or may be idle, but it could be either one thread or the other, and one could be idle. And as soon as you get into these categories, a lot of the calculations internally just go bonkers. I think you've touched point on that with the min-v runtime on a per core granularity, but I'm not sure that's the end of the tunnel yet. I would like to assemble a small Git repo where I can just throw this test case in. Would you be interested to like follow up with me and try to find out how we can make the system actually fair?
Yes, absolutely. All test cases are interesting.
So let's follow up with that one after offline.
Yeah, that would be great. Yeah, looking for that.
Yeah.
Okay,
Also,
cool.
thinking if you could reply to the V6 series with like maybe a summary of all of these problems, that would also trigger some discussion on the list.
Absolutely. The reason I didn't bring it up was mostly because I didn't polish the HRTIC patches to a point where I would actually be happy to send them. And the other problem with the scheduling in general, the test case, I just wanted to give you the test case to actually verify that you're seeing the same problems. Otherwise, it'd just be moaning, right?
Yeah, that would be great. Yeah, so that we can also try and probably work together to come up with a fix for the issue. The fairness issue is a bit of a non-issue, as I mentioned, due to the V runtime comparison and the load balancing. But yeah, there might be something deep which we might not have known. So the test case would be great. Thanks.
Yep. Let's go down together on that one. Cool.
I guess, do we have any other questions or?
Thank you. Does anybody else have any more questions for this team?
Vincent, I guess, did you have any comments on the V runtime stuff? Anything in that area? I think I saw Vincent. Yeah, I don't know if he's on or not. Okay, never mind. Yeah. All right. Thank you very much, everyone.
Thanks, guys.
Bye.
Thank you.
Bye.
Bye. We now have another 15-minute break before the next presenter. Our next presentation is going to start in 2 minutes by Marco. Hi, Marco.
Hello. Can we start or should we wait one more minute?
It's 10 a.m. Here we can start. Data race detection in Linux kernel. Here you go.
Thank you. So hello, everyone. I'm Marco, and I'm part of Google's Dynamic Tools team. And today I'm going to talk to you about data race detection in the Linux kernel. It takes a bit. Okay. So why do we need a race detector? Well, experience has shown that humans just aren't that good at reasoning about multiple threads of execution. A kernel's job is inherently concurrent, but clearly we also want a performant kernel with as few points of contention as possible. But often we have to choose between simple synchronization and more performant synchronization. And in an attempt to optimize synchronization and reduce points of contention in the kernel, numerous advanced synchronization mechanisms are in use by the kernel, where we can also find various ad hoc lockless patterns these days. Given the scale of the code base, mistakes will happen. It also is no secret that the Linux kernel already has tools, such as LockDep, to help debug concurrent code, but no race detector yet. In fact, there have been past attempts at race detectors for the Linux kernel, but none of them made it into mainline. Let's see what we can do about that. In case you were wondering, this presentation is about the kernel concurrency sanitizer. KCSAN was merged into Linux 5.8, and the latest dev version can usually be found on the RCU tree. Work on KCSAN started around July of 2019, and we announced the first draft version in September 2019. To understand how we got here, I'll start with background on what it actually is we're trying to solve. Okay, what are data races? Data races came about because the C language and compilers evolved oblivious to concurrency. There are numerous optimizations that compilers can apply to plain C language accesses that would ultimately break concurrent code. That is, there'd be a problem if the programmer requires and believes that plain C language accesses actually happen as one indivisible atomic step. The solution to this problem is to make the compiler concurrency aware. But how do we still get to keep all the nice compiler optimizations that in the common case are useful and make our code run faster? The best solution we have is to tell the compiler about accesses that will be used concurrently. Data race is defined at the programming language level in a subspecification of the language called the memory consistency model. And since C11, C, and compilers are no longer oblivious to concurrency, they introduced the memory model along with atomics and so on. In C11's world, data races cause undefined behavior, simply because it's too difficult to enumerate all possible compiler and architecture combinations and how various optimizations might behave. I'd say it really is an impossible task to give well-defined meaning to data races. But that's not the Linux kernel's model exactly. The Linux kernel has its own memory model, the Linux kernel memory consistency model, or just LKMM, for various reasons. But in short, it's not straightforward to match the kernel's needs with what C11 would have us do. We also have a written down definition of what data races are. So I'll just read this out. Data races occur if we have concurrent conflicting accesses, and they conflict if they access the same location and at least one is a write, and at least one is a plain access. And plain access is a normal C language access compared to marked operations. And in the Linux kernel, we have various ways to mark operations. For example, read once, write once, SMP load store ops, atomic T ops, and a bunch more. Here we have some examples, and as you can see, all the ones with an X, with a red X, are data races. And you'll notice that for each of them, we have at least one write and one plain operation. The orange X's are a bit special. They're data races according to the LKMM, but current convention has it that marking certain writes can often be forgiven. So why should we care to write data race-free code in the first place? For one, we just have to reason within the bounds of the language and not about what the cross product of all compilers and architectures might produce. In the kernel, we acknowledge that data races may always exist intentionally for performance reasons usually, but reasoning with that code always behaves correctly is very hard, if not impossible. But we also have to realize that there may be a mismatch between the kernel's needs and the language and primitives we have. The other major benefit opportunity we have is that we can use the language to more precisely capture our concurrency design. Obviously, we have to have a good idea of where concurrency is, so why not capture this in our code? For example, accesses that should never be concurrent, yet are observed to race, indicate a symptom of a more serious logic bug or a race condition. Here, a data race would merely be a symptom of a higher level issue. In the end, we want to make the kernel more reliable and make debugging elusive race conditions a thing of the past. Okay, so I want to give an example of how typically a useful optimization can cause harm in a concurrent context. So here we have a function that does 2 repeated loads, dereferencing x, to compare against 0. If the value is non-zero, we'll do some other operations. In the example, we'll store to A and B. A helpful compiler might realize that the repeated loads are unnecessary and fuse them to produce the transformation on the right. That's all well, and for single-threaded code, this is a helpful optimization. Now consider this other function, bad wait, which repeatedly checks the stop condition in a loop. Again, the compiler will recognize that the repeated loads to stop are necessary, and the helpful compiler might then produce the transformation on the right. We only dereference stop once, but then end up in an infinite loop. In a non-concurrent world, this is perfectly fine. But the compiler didn't know that we intended to write to the location at stop concurrently. The transform code is now clearly buggy. Therefore, we need to use primitives that can be used in concurrent contexts and ensure the compiler always produces correct code. In the example here, we should use read once to load the stop condition, which avoids any harmful optimizations. The example here only illustrates one of many ways a compiler might miscompile your code. Okay, so recall that data races can also be a symptom of more serious problems. For some back classes reported by other debugging tools, for example, out of bounds or use after free bugs, it's often obvious that there's a serious problem. But the severity of problems causing a data race is not at all obvious at first glance. So we want to caution against mindlessly sprinkling read once and write once into code. For example, we found a data race in the FATFS implementation, and as non-maintainers of the subsystem, it really wasn't straightforward for us to say what's going on. And we required the maintainer to figure out what's actually happening. In the end, the fix on surface, it doesn't look like something that would prevent a data race. So I do want to stress again that data races can be due to all kinds of interesting and bizarre problems. Okay, some numbers. So the number of known fixes to address data races since KCSAN was announced in September 2019 is around 60. Maybe there are more, but that's the ones I keep track of. And the number of concurrent KCSAN reports on the number of current KCSAN reports on Sysbot is around 350. And the number of reports on Sysbot include moderated reports, and most of them actually haven't been sent to the kernel mailing list yet. This gives us a chance to better understand how to make reports more useful and maybe point out common patterns as we learn them. But currently, this is the biggest challenge and something we really want to find a solution to. There are several ideas, but this will take time. Maybe it's something that we can discuss at the end of this talk. Another statistic is the number of obvious fixes addressing some kind of race. So from 5.3 to 5.8, we've seen around 101 commits that matched the commit title of fix or avoid race. This is not entirely accurate. It gives us a rough idea. Hopefully, CI systems run more and more tests as well as start adopting KCSAN. And we're hopeful that this number will also go down. So now that we understand the problem, let's talk about how to detect data races in the Linux kernel. Okay, so there have been several past attempts, and arguably the most notable one is the kernel thread sanitizer, which was also developed by the dynamic tools team at Google. KTSAN relies on compile time instrumentation and uses the same algorithm as user space TSAN. That is, it happens before race detector. In this case, using something called vector clocks that can be used to order events, such as memory accesses from multiple threads. If KTSAN determines that a memory location's last modification is ordered after some last valid synchronization point, it'll report a race. This also means the accesses do not actually have to be observed to be concurrent. Rather, the absence of synchronization is enough to detect a race. There are several advantages to this. So there are fewer false negatives. It's a lot more precise, and it can also detect memory ordering issues, for example, missing memory barriers. But this also comes with a cost, which is scalability, the required memory overhead, and that false positives we have false positives without annotating all synchronization primitives, which is particularly tricky in the kernel. So there are many more attempts at race detection for the kernel, but another interesting one is RaceHound, or rather a data collider. So RaceHound itself is a close implementation of the data collider approach published in an OSDI paper in 2010. Data collider relies on hardware memory breakpoints. So for memory operations, it sets up a hardware breakpoint, but then stalls the memory access for some delay. If the breakpoint triggered, a race was observed. So it also checks the value before and after the delay, and the value change is inferred to be a race. So why did KTSAN and these various other approaches never make it into the mainline kernel? So I'm going to argue that it's about designing something that automatically scales to and evolves with the kernel code. So the first requirement is about runtime performance. So the data collider approach has very little overhead by design. Although KTSAN's algorithm is not cheap, the user space version of TSAN has shown that it can be made really performant. The second requirement is we'd like to have a low memory overhead. So unfortunately, KTSAN requires several gigabytes of metadata. The third requirement is we want to prefer false negatives over false positives. And I think this one is very important because kernel developers are busy people, and we need the human effort to act on reports to scale. Which leads to the next point, which is we want the solution to be unintrusive to the kernel. That is, we want to avoid excessive annotations. And especially in the kernel, with numerous synchronization mechanisms, trying to keep up just wouldn't scale. KTSAN unfortunately requires precise annotations to avoid false positives. And the fifth requirement is that we want scalable memory access instrumentation. So RaySound requires manually placing K-probes, whereas the original data collider approach actually used a post-processing step over assembly and selecting memory accesses. The best approach here is to simply rely on the compiler to insert instrumentation. Which leads me to the last point, which is that we want our tool to be language level memory access aware. And so what does this mean? Essentially, can the tool be made fully aware of and distinguish between source level language accesses? This is especially important because we want to be able to teach the tool the rules of the memory model. In our case, the Linux kernel memory model. We want the tool to insert instrumentation that distinguishes plain and different types of marked accesses. This really suggests that we need support from the compiler, since the compiler has precise information about language level accesses. So can we combine the best of both worlds? And I'm going to show you how KCSAN satisfies all our requirements by combining both of these approaches. So KCSAN is a dynamic race detector that detects races at runtime. So all you need to do to use KCSAN is configure your kernel with config KCSAN set to yes. And there are numerous other options to tweak precise behavior. For example, for very large machines, you might want to increase the sampling interval. Currently, only the 64-bit x86 architecture is supported, but hopefully we'll get ARM64 support in the near future. In general, the core code is generic, and there are no architecture-specific bits. Porting to a new architecture primarily needs testing and very likely disabling instrumentation for a bunch of code, like early boot code. To compile the kernel with KCSAN, we need a fairly recent compiler. The first release of KCSAN in Linux 5.8 was Clang 11 only, but as of Linux 5.9, GCC 11 will be supported as well. Clang 11 should be released soon, hopefully, but GCC 11 is still in development. We initially designed KCSAN to work with all compilers that support F-sanitized thread, but to merge KCSAN into 5.8, this unfortunately had to change. On the right is what you can expect a KCSAN report to look like. It starts with the title that summarizes the two functions where the racing accesses occurred, which is followed by more detailed access information, including the operation, such as read-write, and if the operation is marked, the size, and then the context and CPU. Optionally, if you have lockup enabled, KCSAN also shows you the currently held locks. So now let's have a look at how KCSAN actually works. So the very basic idea is that we want to observe two accesses happening concurrently. The important property of this approach is that we catch races precisely when they happen. So that is when KCSAN reports a race, you can be certain that the race it's showing you just happened. and the two accesses it's pointing at just executed concurrently. So this can either be because the accesses are executed in parallel on different CPUs. It could also be due to executing concurrently on the same CPU due to an interrupt. So how do we select accesses? So we let the compiler instrument all memory accesses reusing the TSAN instrumentation. As mentioned, one other requirement is that the tool should be aware of the source language level accesses, so that we can teach the tool the rules of the memory model. Relying on the compiler for this gives us all the information we need to distinguish accesses. For example, we tell the compiler to emit different instrumentation for read once and write once. So how do we catch races? We rely on stopwatch points. The details explained are after this slide. The idea is to set a watch point for the address and stall the access. If some other conflicting access overlapping with an overlapping address finds that a watch point exists, we just observe the race. We also check the value before and after the stall. If the value changed, we again infer a race, but might not know which the other racing access was. The delays are random to increase the chances of observing a race if some code is executed repeatedly. The default delays are on the order of microseconds, but these can be tweaked via kernel boot parameters or even at runtime. So you can boot the kernel with, say, a very performant config and then tweak it, say, if you're running a test case. Watch points are set for all instrumented memory accesses. An important property of the watch point-based approach is that not instrumenting an access will never result in false positives. And finally, we need to decide when to set up watch points. This is done periodically, skipping over some number of accesses before the next watch point is set up. In the default config, a watch point is set up on average every 2000 accesses. This is a uniform random distribution we've chosen there. Okay, so now let's have a look at the flow through the core runtime. So for an instrumented access, given some address, its size, and the type, we'll first try to find if a watch point has already been set up. If a watch point already exists, this will lead to a report. If no watch point exists, we'll see if we need to set up a watch point for this particular access. So find watch point also matches, matches based on overlapping memory accesses, and if the other access would conflict. And a conflict can only occur if we have at least one write. So now let's assume we have not found a watch point. In this case, we'll proceed to check if we should set up a watch point for the access. That is, should we sample this access? If we should not sample the access, we'll just exit the runtime and proceed. But it's not only whether or not we should sample the access. This also is the place where we implement details of the memory model. For regular plain accesses, we can always set up watch points. But for marked accesses, we should never set up watch points. And that way, we'll never detect races between two marked accesses because neither will set up watch points. Okay. So if a watch point should be set up, we'll enter the slow path. Here we set up a watch point, then introduce a delay. After the delay, we check if the watch point was found, or we observe the value change. If either is true, we'll generate a report. Otherwise, we couldn't observe a race and just exit the runtime. And that was the overview of the runtime. Okay, so KCSAN relies on soft watch points, as I had mentioned earlier. So rather than relying on the hardware watch points. So this provides several benefits. In particular, we're more flexible, the code is portable, and it scales to any number of concurrent watch points, for example, on very large machines. The soft watch points are implemented with an array of longs, specifically atomic longs, where each entry can have 3 states. A watch point is either invalid, a valid encoding of an access, or it has been consumed. We index into the array based on the addresses page. If an entry is not in the invalid state, another watch point that would map to the same index may spill into adjacent slots. KCSAN collects statistics on how often no usable slots are available, and the defaults are chosen so that we typically have a usable slot. So if a watch point is valid and a racing access found the watch point, the racing thread will consume it. This will signal the thread that set up the watch point that a race occurred and enter the reporting logic as explained in the previous slides. We only release the watch point when exiting the runtime after report generation. And this is important to avoid deadlocks, as the same watch point index is used to set up the report information producer and consumer. A lot of complexity is actually hidden behind the reporting logic, which I won't go into here. Okay. We use a special encoding to save space, but also avoid multiple fields, which would require lock-based synchronization. The initial motivation for compressing the access information in this way was to enable the use of atomics. So we require 1 bit to store if the access is a write or not. We use 14 bits to encode the size for accesses up to 16 kilobytes. And then the remaining bits are for the address. On most architectures, we can easily get away with discarding the upper bits of an address and never run into false positives. On the off chance that we do get a false positive due to address encoding, the reporting logic will sort it out. And these constants for the number of bits are actually dependent on page size and bits per long. Okay, so KCSAN's focus is on data races, but why stop here? All the logic to detect races is already there. So let's look at this example. Here we have a critical section protected by the update foo lock. In there we have a marked write and a comment. The comment indicates that concurrent readers are okay, but if the lock is held, there should be no other writers. Therefore, this concurrent read once is perfectly fine. But this concurrent write once is not. None of these accesses are data races. And the buggy write, due to being marked, is no data race either. Wouldn't it be good if we could turn the comment from thread 0 into something that KCSAN could check for us? KCSAN provides the assert exclusive family of macros, which lets us do exactly that. And we can then check that there really are no concurrent writers, marked or not. There are a few types of assert exclusive checks. The main use, as mentioned, is to check concurrent code, where some bugs would never be data races. This was the result of early discussions where it became clear that data race detection alone was not enough to check complex concurrency designs. And since KCSAN already has all the logic to detect races, it was only a matter of exposing this functionality in a useful interface. There are 3 main types of assertions. Assert exclusive writer can be used to check that there are no concurrent writers while allowing concurrent readers. Assert exclusive access checks that there are no writers nor readers. And both of them have a scope variant, which is useful to perform the checks through a whole block of code. And finally, assert exclusive bits, which checks that there are no writers to the bits in mask but concurrent writes to any other bit is allowed. More details on these can be found in the documentation. To conclude, okay, so for KCSAN and all the bits around it, without continuous feedback from the community, we wouldn't have gotten anywhere. And we started development on KCSAN around July of 2019. And at that time, we only had the LKMM and some assumed requirements and preferences to go by, and maybe some past learnings from KTSAN. We sent the initial version in September 2019, and then started to iterate. And there were several discussions, and here are some examples of what came out of these discussions. So for example, the config KCSAN report value change only config option was the result of an early discussion with Linus. That option is to deal with the case where the same value is written over and over, even if those writes can happen concurrently. Since it's the same value that's written again and again, the assumption is that no harm can be done. The other is the data race macro, which came about in the same discussion. That is to mark intentional data races, of which there are quite a few in the kernel. And as I mentioned in the beginning of the talk, we have an option called config KCSAN assume plain writes atomic. If that's on, which it is by default, then plain aligned writes up to word size will be forgiven if not marked. And finally, we have config KCSAN verbose, which shows health logs in reports if logdep is enabled. This feature was also not part of the initial version. So we also have a bunch of open questions, and maybe they can be discussed at the end of this talk. So for example, how should we report data races from CI systems, for example, Sysbot? So currently this requires moderation from us, but we also do want expert eyes because we just don't know what to do with some of the reports. So should we keep sending them one by one, or should we batch data race reports from subsystems? Maybe that'll reduce the overhead somewhat. And how can we deal with the other point that I'm currently dealing with is how to deal with plain read modify writes. So there are a lot of concurrent uses of plain read modify writes in the kernel. Some can safely be marked with data race, but in some other cases, it's really hard to say if it's safe. So, but in those cases, sometimes it's also the case that we shouldn't, or I don't know, for some reason we can't use atomics for performance reasons. So what should we do in that case? I don't have an answer to that. So, and that concludes the talk. For even more details, I highly recommend the two-part LWN article, Concurrency Bugs Should Fear the Big Bad Data Race Detector. There's also a backup slide in case you're interested in seeing some interesting bugs or want to see some of them, but I won't discuss these here. Otherwise, thank you for listening, and I'm happy to take questions now. And I think we have about 10, 12 minutes for a discussion.
There's a question in the chat. Some of these would seem like CVE candidates, this being the KCSAN reports of these issues.
Which ones? The ones at the end of the slide deck? Or all of them? Oh, right. Okay. Yes, that's why I put them there. I mean, some of them have been fixed. The ones that haven't been fixed, it would be good to fix them, but I think, what was it? Let me have a look at one of the unfixed ones. Right. The one where I say task dump owner. Yeah, that one's interesting. I think we had a discussion about that one, and there was no consensus how to fix it. Yeah. Maybe, yes. I don't have an answer, unfortunately. But yes, you have a good point.
Quick question. You mentioned the need to remove use of atomic operations for some use cases because those were too slow. Could you use split counter approaches where you keep track of stuff in per CPU counters and then aggregate that in a sampling way after the fact or gradually?
Right, that's a good point, and that's, I guess that always depends on the use case. The point that I was making is that there are a lot of these plain read, modify, write uses. I mean, those are there right now, and an obvious solution would be to use an atomic or atomics, but often we get pushback and say, no, atomics don't work because it's too slow, right? And yes, you have a good point there, but again, this is really dependent on the use case, and I don't know, it depends. It's a case-by-case thing. And there's no pattern, at least not one I'm spotting yet. And I also see. Go ahead.
Sorry.
No, please go ahead.
From having looked into some of these recently, while trying to enable this on ARM64, a lot of the uses of unmarked read, modify, writes. The reason for not using atomics is that they didn't really care about the end result value. They just they just wanted to catch where a value is changing significantly over a window of time. So actually, that's something we could probably fix with a new type that's distinct from atomic, that's allows like the W to occur, but even if it's just like a read once, write once wrapper. And I think most other uses of unmarked RWs are simply just bugs and misunderstanding.
Yes. So I think, yes, also some of them probably can be just marked data arrays, but others, I don't know. So there's also the one that I recently looked at was non-atomic bit set and bit clear. And we actually determined that there, if you're just modifying a single bit, it seems this is fine to use concurrently, but I still need to convince myself fully. But yeah, there might be new primitives we're missing, and as I hinted at earlier, right, there may be a mismatch between what the kernel, like the language we're currently using. Well, we have a dialect of C, but essentially the primitives and the version of C that we're using is missing something for certain things. And I don't know how extensible or how much we can add with macros and so on. But yes, that's a good point. Can you give an example of a bad read modify write? I mean, I think if you're doing something like, okay, variable plus equals something else, and you're expecting this to be safe in a concurrent context, you first have to understand what the compiler is doing. And then you also have to understand what the architecture is doing. For example, if you really say, if you're expecting to read unique values when doing, say, an adding or increment or something, and doing this non-atomically, then you have a problem in case, for example, on x86, you actually require cache line locking. If you have that, for example, if you have a concurrent other writer or some other thread that's trying to increment the value, you may actually end up reading some garbage. The same with the compiler. The compiler might end up doing all kinds of interesting things, and I actually can't tell you what it might do. But I think the increment cases and decrement and all these there are usually interesting. The bitwise operations, again, I don't know. I would just say use the proper bitops that the kernel provides, because there we actually control what's happening compared to relying on the compiler for something. That was a longer answer to your question. I see a question, is there any future plan for KTSAN? That's a good question. I think right now the project is on hold. The wiki page also says the project is unfortunately on hold. And I think there were, as I mentioned in I guess the summary of KTSAN is that there are a bunch of problems in getting this working, and I think the biggest one is trying to keep up with all the possible points of synchronization that can happen in the kernel. And this really, I mean, as the kernel changes and moves so quickly, trying to catch up is difficult. So unfortunately, it is on hold right now.
So is there a possibility that we can use it for, we can use the hardware watch point and use it for selected set of, say, variables which we somehow see are being under some race rights?
So are you suggesting that we could use hardware watch points as an optimization or replace the current?
As an optimization also, and not enabling for the whole kernel, but if we feel that, if I'm just thinking from a debugging perspective that, if we feel that a particular variable is getting corrupted in certain scenario and we want to debug it, can we use this one, not for the whole kernel, but for that particular one, and not using the sampling? Maybe it's not a frequent race, right? It's a one time or very, very infrequent one, and we use the hardware watch point.
Right. So I can imagine that you could probably bolt on hardware watch points in some way to maybe for some optimizations, but you're still going to end up with something very similar. And I also don't know what the overhead of the hardware watch points will be. And I found when I was investigating this that they were very limited. And essentially the soft watch points that I have there are a lot more flexible. You can just have tons of them. The hardware watch points, I mean, you can also, for example, if you're suspecting that you might have a variable where there's a race or there's a corruption, you could try and use the assert exclusive macros to see specifically for that variable. And then I mean, it's not yet as ergonomic, but you could disable instrumentation for KCSAN instrumentation for all of the kernel except the portions of code that you're interested in. But I don't know if that's exactly what you were after.
And you mentioned that it will be soon available for ARM64. Any target?
I unfortunately don't know this. You'd have to ask Mark Rutland, who is helpfully trying to provide this. But I don't think there's no promise yet. Hello.
Yeah. Sorry, there are just a few bits and pieces. I have preparatory patches that I was planning on sending out this week, but as I've broken my arm, rebasing them's a little bit painful at the moment. So those will probably come out to the list in the next couple of weeks.
Oh, sorry. No, it's no rush. So, but thank you. Thank you very much.
Mark, did you break your arm performing the rebase?
I fell over on a lawn. Much less exciting.
I see a question. One second. Were you able to measure overhead of enabling KCSAN on production workloads? So I did some benchmarking initially. I found that I think the overhead was something like 3 to 5x, at least for the kernel. But I think in general you can run KCSAN. I actually, at one point, this was for a very, very early version of KCSAN. I took a development version of KCSAN, compiled the kernel, and put this onto, I think, my desktop where I usually play games on, and I just booted it. It seemed to work. But other than that, I haven't done any other experiments. Also noticed that actually recently KCSAN has gotten a bunch of optimizations. For example, the initial version that I benchmarked had like function entry and exit instrumentation, and all this has been removed in the version that was merged into 5.8. So I would expect it to be a lot more performant than it was like half a year ago. Thank you. I think we have 2 minutes.
Thank you very much. Do we have any other questions remaining?
Oh, right. Okay. Well, with 5.8, yes, it's Clang only. But as of 5.9, we'll have GCC support again. But of course, GCC support. Well, GCC 11 is still in development. I expect it to be. Well, I don't know how these releases work. Maybe next year we'll have a release for GCC that will then also support KCSAN. In the meantime, the patch. If you're curious, send me an email. And I have instructions how you can build a GCC 10 with for KCSAN. There's a question, how much CPU overhead is required? What is the question directed at? Oh, right. I guess you mean compiling the kernel. Well, we have to, the compiler will run all the thread sanitizer passes. So it's not completely free, but I would say it's I still build my kernels in under 2 minutes if I enable all 64 cores to compile for me. But I haven't done any rigorous studies on compile time overhead.
Thank you. I think that's all the time we have for this presentation.
Okay, thank you.
Have a wonderful day.
Thank you. Yes, thank you. You too. Do we stay here or do we log out? I guess this was the last one, right?
This was the last one of the day, so we can log out and end the presentation.
Okay, thank you all for listening.
You are currently the only person in this conference.